Hey everyone, welcome into Unit 8, Day 13 Notes. Today we are going to be factoring with special cases. So far this unit we have factored when A equals 1, and we've factored when A does not equal 1. And today we're going to be looking at factoring but with special cases. Our goal today is that students will be able to factor with special cases with 80% accuracy. So let's get into it. When factoring, there are two special cases that you may come across. Special case number 1, we call it a difference of perfect squares. So without me even showing an example or going into things to recognize, let's just break that down. So difference in math is subtraction, and then perfect squares. So perfect squares are numbers we can take the square root of and get a whole number. For example, the square root of 100 is 10. The square root of 121 is 11. One more, the square root of 36 is 6. So subtracting perfect squares, difference of perfect squares. So the first thing to recognize is that we must have a binomial, right? Two terms. The second thing we need to notice is that both numbers are perfect squares. And then the third thing, we mentioned it already, there must be a minus sign between those perfect squares. So difference, minus sign, perfect squares. And for this unit is the only time that we are going to be factoring binomials unless we have a GCF. So steps of factoring, we did discuss in previous notes that we always start with a GCF. So I'm just going to write that up here. Start with GCF. Okay, if we don't find a GCF, then we continue. If we do find a GCF, we factor out the GCF and then we continue. So, but there are new steps for factoring this special case is that we just take the square root of the first term. So the first term is 25x squared. So the square root of 25 is 5, and the square root of x squared is just x, because x times x is x squared. And we are going to jot that down as our first term in each of our binomials. All right, next step. Signs that we're going to put in are opposite. So signs meaning plus and minus, opposite signs. Step 3, we square root the second term. So square root of 49 is 7. So we have 5x plus 7, 5x minus 7. And that's it. That's all there is to it. So the recognition, checking for GCF, and then knowing your perfect squares. So we're going to work on 1, 2, and 4 together. Number 1, is there a GCF? We say no. There's no number that goes into 25 and 36. So we continue with our steps. It's a binomial, perfect. Both numbers are perfect squares. So we take the square root of the first term. The square root of 25 is 5, and the square root of x squared is x. The square root of 36 is 6. So we have 5x plus 6, 5x minus 6. And that's it. Difference of two perfect squares factored. Next one. Again, there is no GCF. We do have x squared, and there is a 1, right, invisible 1 in front of the x squared. And 1 is a perfect square, and x squared is a perfect square. So we get square root of 1 is 1, and the square root of x squared is x. So we have 1x plus, and we're going to have 1x minus, opposite signs. The square root of 9 is 3. And there we have it, x plus 3, x minus 3. And again, you can always double check to see if you're getting these correct by double distributing, and you'll see that the middle terms will cancel out. Actually, we will take a look at that example when we do number 4. We'll go through checking it, number 4. So our GCF, again, there's no GCF for this one. So we go ahead and take, okay, we have a perfect square of 49 is 7. We have a perfect square of x, which is x. But take a look at our binomial. There is a plus sign. And we need it to be a difference of perfect squares. So this is not a difference. I'm going to double underline that. This is not a difference of perfect squares. So we can't use our little trick to factor this. And therefore, because there's also no GCF, this is going to be prime. Okay, go ahead, try 3, 5, and 6. Come back and we'll see how we do. See you in a few. Okay, let's go ahead and take a look at number 3. So if you did this one real quick, you might not have noticed that we do have a GCF of 4. And now you could have factored it without doing the GCF, but then you would have had a GCF within that, within those binomials. So you would have had to have factored out GCF later. So it's always good to check for that GCF first to get it over with and take care of that business right away. So we have a GCF of 4, and when we take out that GCF of 4, we still notice that we have a perfect square of 4x squared, and then a perfect square of 1. 1 is a perfect square because the square root of 1 is 1. So don't forget that GCF should come down on the outside, and then we have the square root of 4 is 2. Square root of x squared is x, so we have 2x plus 1 and 2x minus 1. I did not mention this earlier, but just to take a note right now, is that the plus sign and the minus sign do not have to go in the order that I put it. So if you did 2x minus 1 and then 2x plus 1, that is totally okay. All right, let's go ahead and take a look at number 5. So number 5, 4x squared minus 81. There is no GCF. The square root of 4 is 2. Square root of x is x. Square root of x squared is x. Square root of 81 is 9. So 2x plus 9, 2x minus 9. And now I did say we would check our answer for number 4. I would show you how to do that, but it was prime. So we couldn't do that. So let's just show here. We're going to check it here. We double distribute. 2x times 2x is 4x squared. 2x times negative 9 is negative 18x. Then we get a positive 18x. Then we get a minus 81. And so again, our middle terms are going to cancel out. That's why one of our signs has to be plus and one of them has to be minus, because that will make our middle terms cancel out, which will leave us with 4x squared minus 81, which is where we started. And that's how we know we're correct. Okay, and then number 6, there is no GCF. I checked for GCF. I just didn't write no, but there's no GCF, and we get 13x plus 10 and 13x minus 10. All right, let's take a look at special case number 2. So special case number 2 is that it's called perfect square trinomials. So we need perfect squares again, but this time we have trinomials, not binomials. So trinomials are 3 terms. First thing we need to look for. Second thing, the first and last terms are perfect squares. The last sign has to be a plus sign. So if we take a look at our example, first we're going to say, hey, is there a GCF? Always look for that first. There is no GCF. Then we say, okay, it's a trinomial. I need to notice that the first term is a perfect square. The last term is a perfect square. And that there is a plus sign as our last sign. If that is the situation, if those things line up, then we have our second special case, in which, in order to do that, very similar to the first one, first special case, we take the square root of the first term. So the square root of 9 is 3. The square root of x squared is x. So you have 3x and 3x. The second thing we do, signs are the same, but we're going to use the first sign. So we're looking at this one right here. We already have 3x and 3x. And because that first sign is a minus, we're going to make both of our signs a minus sign. Step 3, square root the third term. So the square root of 16 is 4. 3x minus 4, 3x minus 4. Now we've talked about this before. Rewrite your answer. Because we have 3x minus 4 times 3x minus 4, we're going to rewrite it 3x minus 4 squared. Anything times itself is squared. And we looked at examples like this when we were double distributing at the beginning of the unit. Remember, our trick was that we had to write it twice. You could not just distribute that exponent to the rest of the parentheses. So 3x minus 4 times 3x minus 4 is 3x minus 4 squared. And that is how you need to write your final answer. All right, let's take a look at a few examples. Let's take a look at number 1. So we always check, is there a GCF? We say no. There is no GCF here. So the square root of 64 is 8, and the square root of x squared is x. The square root of 9 is 3, so we're going to have 8x. It's a plus sign, so we know we can do this, and we're going to take the first sign. So 8x minus 3, 8x minus 3. And then we rewrite our final answer, 8x minus 3 squared. And there we have it. All right, let's take a look at, let's do number 2. So first things first, there's no GCF. Then we take the square root of 81 is 9. The square root of x squared is x. We notice that that second sign is a plus sign, so we can do this. The square root of 49 is 7. So we do 9x. We do minus, because that first sign is minus, 7. 9x minus 7. And then rewrite our final answer, 9x minus 7 squared. All right, let's go ahead and do one more together. Let's check out number 3. There is no GCF, and our second sign is a plus sign. So we do the square root of our first term, which is 1x, 1x, and the square root of our second of 36 is 6. So do x. We are going to take the sign of our first sign is a plus sign. So x plus 6, x plus 6, and we rewrite it x plus 6 squared. All right, go ahead, try examples 4, 5, and 6. Come back and see how you did. See you in a few. All right, welcome back. Let's go ahead and take a look at the answers to 4, 5, and 6. So the answer number 4, there is no GCF. We know this method can work. Our special case, because our second sign is a plus, we know our first and last term are perfect squares. So we get 10x plus 3, and rewrite your answer as 10x plus 3 squared. Number 5, same deal. There's no GCF. Our first term is a perfect square. Our last term is a perfect square. And then we have that plus sign. It's 8x minus 3 this time, because if all that is true, we have the special case, and that means that we take our first sign. So it's minus, so that's why it's 8x minus 3, 8x minus 3. And then same deal with number 6. First term is a perfect square. Last term is a perfect square. We have a plus sign there. And then we're going to take our first sign when we write our factored binomials. Okay, nice job. I hope this was okay for everyone. Please make sure that you reach out to your teacher if you have any questions. Have a great day. Peace out.